There are several properties of logarithms that we want to explore. The first one is the multiplication property of logarithms, and it says that if m and n are positive real numbers, that if we take the logarithm of some base, in this example a, of the product of m and n, that this is going to be equal to the log base a of m plus the log base a of n. In other words, when we take the logarithm of a product, that's the same thing as the sum of the logarithms of the factors, right? M and n being the factors. So we can separate a logarithm of a product into the sum of two separate logarithms, right? So that's the first rule. And we want to prove this. And so to prove this, let's start by letting log base a of m be equal to p. Let's say that p is equal to log base a of m. And let's let q be equal to log base a of n, right? So log base a of m, we're letting that be equal to p. Log base a of n, we're letting that be equal to q. And so let's rewrite both of these in exponential form. This says that a to the p power is equal to m. Right, so we can convert a logarithm into an exponential. Same thing over here. This is a to the q. That'll be equal to n. And so when we look at the product of m and n, m is a to the p, and n is a to the q. And when we multiply two powers, if they have the same base, we add the exponents. And so this is the same thing as a to the p plus q. Right? So anytime we multiply exponentials, if they have the same base, we just add the exponents. That's a rule that you should have learned in a previous class, and hopefully you've remembered that. And so that means that m times n is equal to a. Let me write this out. M times n is equal to a to the p plus q power. Right, so I have an exponential form of an equation. I can rewrite this as a logarithm. The logarithmic form says that the log of base a, right, that's the base, of m times n is equal to the exponent, p plus q. Right, so now I've rewritten this exponential equation in a logarithmic form. And remember what p and q were originally. So the log of base a of m times n is the sum of p plus q. Well, p was log base a of m plus q was the log base a of n. And so this is a proof of the multiplication property of logarithms. And again, it says that if we take the log of a product, that we can rewrite that as the sum of the logarithm of the factors. The second property is the division property. It's very similar. It says that if m and n are positive real numbers, that the logarithm of a quotient, m divided by n, is equal to log base a of m minus log base a of n. And so in other words, if we're taking the logarithm of a fraction, we can rewrite that as the difference between the logarithm of the numerator and the denominator. Now subtraction is not commutative, right? This is not the same thing as, I can't switch the order. I can't say that log base a of n minus log base a of m, right? The order is important when I subtract. The order is also important when I divide. And so notice that the numerator being m comes first, and then the denominator being n comes second. Right, so it's always got to be the log of the numerator minus the log of the denominator. I can't switch these around. It's not commutative. And so we're going to do something very similar. Let's start by saying that p is equal to log base a of m. And let's let q be equal to log base a of n. And so again, I can rewrite these as exponentials. This says that a to the p power is equal to m. And this says that a to the q power is equal to n. And now we are looking for the quotient of m over n. And so m is a to the p power, n is a to the q power, and when we divide exponents, or powers, we subtract the exponents. So this is the same thing as a to the p minus q. Right, so anytime I have two powers, they have the same base, which is a, and I'm dividing them, that's the same thing as a to the p minus q, right? And again, it's numerator minus denominator. The order here is important. And so that says that m over n is equal to the to a to the p minus q power. And so this is an exponential. I can rewrite this in logarithmic form. Logarithmic form says that the log of base a of m over n will be equal to the exponent p minus q. And again, p was log base a of m, and q was log base a of n. And so I'll plug those values back in. The log base a of m, oops, I was supposed to write n here, not p, m over n. The log base m over n is equal to p, which was log base a of m, minus q, which was log base a of n. And so this is the proof for the division property of logarithms. And again, it says that if we're taking the logarithm of a fraction, or a quotient, right, we're dividing something. If we're taking the logarithm of a quotient, that's the same thing as the difference between the logarithms of the numerator and the denominator. And so, again, just make sure that you're careful with the order. Whatever the numerator is, that has to be the first logarithm. Whatever the denominator is, that's what we're subtracting. This is the third property of logarithms. It's about powers, or exponents. It says that if m is a positive real number, and n is any real number, that if we take the logarithm base a of m to the power of n, that's the same thing as n times log base a of m. In other words, if we're taking the logarithm of an exponential, we can take the exponent out front and make it a multiplier. Okay, and so to prove this, we're going to say let's let p be equal to the log base a of m. Okay, very similar to what we did before. And we'll rewrite this in an exponential form. And so this says that a to the p power is equal to m. And so now what we want to do is let's raise both sides of this to the n power, which we're allowed to do, right? Whatever I do to one side, if I do to the other, I'm allowed to do that. So let's take each side of this equation and raise it to the n power. Now, when you have an exponential raised to another power, you multiply this outer exponent times the inner exponent. Again, that's a rule that you should already know. And so this reduces to a to the pn power, right? So we just multiply these together, is equal to m to the n power. Okay, and now we can rewrite this in a logarithmic form, which is going to say that the log base a of m to the n power is equal to p times n, right? And so the log base a of m to the n power is equal to this exponent p to the n, right? So that's how we change exponentials to logarithms. And remember what p was. P was log base a of m. So this says that the log base a of m to the n power is equal to p times n or n times p. I'm allowed to switch them when they're multiplied, right? So I'm going to switch them. I'm going to write the n first. And then p was log base a of m. And that's a proof of this property. So again, this says if we're taking the logarithm of some base of an exponential, that's the same thing as that exponent times the log of that base, right? So the exponent can come out and become a multiplier. There are two special cases of the powers rule of logarithms. The first one deals with roots. And so with roots, we're saying that, for example, that the log of base a of the nth root of m is going to be equal to 1 over n times the logarithm of a of m, logarithm base a of m. And so the way we come about this is that the nth root of m is the same thing as saying m to the 1 over n power. And so anytime we take a root, whatever the index of that root is the denominator of the exponent. And so the rule says that whatever the exponent is, we can bring out as a multiplier. And so here the exponent is 1 over n. We can bring that out as a multiplier, and that will give us 1 over n times the log base a of m. Now the second special case is if n is equal to 0. And so what we're saying here is that if we're looking at the log base a of m to the 0 power, right, where n is 0, that this will be the same rule. We can bring this out. 0 times the log base a of m. Now, 0 times any number is 0. We're going to get 0 over here. Over here, though, if we look at this, any number to the 0th power is 1. And what this is saying is that the log, no matter what the base is, of 1 is always 0. And let me rewrite this as an exponential form to help prove that to you. This is saying that a to the 0 power is equal to 1. And we've already discussed this earlier, that any number to the 0th power is always going to be 1. And so if the exponent inside of a logarithm is 0, that always reduces to 0. So the log of any number to the 0th power is going to be the same as log of 1, and that's always going to be 0. Now there's a third property of the powers of logarithms I almost forgot to include. This would be property C, or I'm sorry, special case C, right? This is the third special case of powers. And the special case is what happens if n is equal to negative 1. And so let's say that we have log base a of m to the negative 1 power, right? N is negative 1. And so if the exponent is negative 1, recall that any number to the negative 1 power is the same thing as 1 over that number to the positive 1 power, right? So x to the negative 1 power is 1 over x. It'll be the same for m. And so the log base a of m to the negative first is the same thing as log base a of 1 over m. And we already know from the power rule that the exponent can come out to the front. So for log base a of m to the negative first power, that is going to be the same as negative 1 times the logarithm base a of m, right? Because the exponent just comes out to front to be a multiplier. And so that means that these are equal. So anytime we take the logarithm of a fraction, we can bring out a negative 1 as a multiplier and take the reciprocal of that fraction, right? So 1 over m becomes m, and we have to bring a negative 1 out front, and these will be equivalent. This is the third special case of the powers property. This is example 1. It says, write log base 4 of 2x to the 5th y squared as a sum of multiples of single logarithms. And so basically what they're saying here is they want us to apply the rules of logarithms that we just discussed. And so when you look at this logarithm, log base 4 of 2x to the 5th y squared, notice that the argument of the logarithm, this part of the problem, right, this is what we're taking the log of, that the argument involves multiplication. This is 2 times x to the 5th times y squared. And so the multiplication property says that if we're taking the logarithm of a product, things being multiplied together, that we can separate this out into the sum of logarithms of the individual factors. And so this is going to become log base 4 of 2 plus log base 4 of x to the 5th plus log base 4 of y squared. And so if we had 2 times x to the 5th times y squared, I could write that out as 3 separate logarithms, 2 x to the 5th and y squared. Notice that the base is always the same, right? The base is always to the 4th. And so we want single logarithms, which we have now, right? Logarithms of just single values. But we want them to be multiples of single logarithms. That means they want us to apply the exponent rules here. And so there's no exponent in this one. That'll stay the same. Log base 4 of 2. But here we have an exponent. And the rule is that the exponent can come out to the front. So this is going to be plus 5 logarithm base 4 of x. Same thing here. We have an exponent. The exponent comes out and becomes a multiplier. That's what they mean by multiples. It's going to become 2. This is going to become 2 log base 4 y. And so this is an equivalent expression for log base 4 2x to the 5th y squared. That becomes log base 4 2 plus 5 times log base 4x plus 2 times log base 4 y. This is example 2. It says write log base 3 of radical x times x minus 2 divided by x plus 3 squared as a sum or difference of multiples of logarithms. And again, they want me to apply the rules of logarithms to sort of simplify this equation or break it out into single logarithms. And so the first thing we want to do is log base 3. We want to get rid of the radical. And so to do that, we need to remember that the square root is the same thing as raising all of this to the 1/2 power. Okay, raising all of this to the 1/2 power is the same thing as square root. And so that's what I want to do first. Okay, and then I need to remember that when I raise a product to a power, that I'm going to raise each factor to that power, meaning that the exponent sort of distributes to each factor within the square brackets here. And so this is going to become x to the 1/2 power times x minus 2 to the 1/2 power, all divided by x plus 3 squared. So my first goal was to get rid of the radical and distribute the exponent if necessary, which I've done. Okay, and now we can start to break this up into sums and differences. Remember, anything that is being multiplied inside the logarithm is going to become a sum of logarithms. Anything that is being divided is going to become a difference. And so this is going to be equal to the log of base 3 of x to the 1/2 power. And because it's being multiplied, it's going to be plus log base 3 of x minus 2 to the 1/2 power. And then because this is being divided, it's going to become subtract log base 3 of x plus 3 squared. Okay, and now the last thing that I need to do is apply the powers rule. I want to get rid of the exponents by bringing them out front and becoming multipliers. So this is going to become 1/2 log base 3 of x plus 1/2 log base 3 of x minus 2 minus 2 log base 3 of x plus 3. Okay, and that will be the solution. This will be the simplified version of that original logarithm. This is example 3. It says write 3 log base 2x plus 4 log base 2y minus 2 log base 2z as a single logarithmic expression. And so here they want me to do the opposite of what we did in examples 1 and 2. This time we have an expression that is the sum or difference of multiples of single logarithms, and we want to combine that into just one logarithmic expression. And so I should start by saying that this only works because the bases are the same. This only works if all 3 bases are 2. Okay, I can only combine logarithms into single logarithms if the bases are the same. And so the first thing I want to do is I have to get rid of the multipliers. I gotta put these up as the exponents inside the arguments of the logarithms. So this is going to become log base 2 of x to the 3rd, right? The 3 becomes the exponent, plus log base 2 y to the 4th, 4 becomes the exponent, minus log base 2 of z squared. Again, the exponent, the multiplier becomes the exponent. Now that I've gotten rid of the multipliers out front, I see I have pluses and minuses. I can rewrite this as a single logarithm of multiplication and division. So anything that's being added will be multiplied, anything that's being subtracted will become division. And so the single logarithm will be log base 2 of x to the 3rd, y to the 4th. Again, they were being added, so I multiply them. This is being subtracted, so I'm going to divide by z squared. This is example 4. It says write 3 log base 10 of x minus 1 minus 1/3 log base 10 of x minus log base 10 of 2x plus 3 as a single logarithmic expression. And so again, they want me to do the same thing. They want me to write this as a single log of some argument. Just like last time, the first thing I need to do is get rid of the multipliers by making them exponents. And so the 3 will become an exponent. It will be log base 10 of x minus 1 to the 3rd power minus log base 10 of x to the 1/3 power. So the 1/3 became an exponent. And there's no multiplier here, so this will stay log base 10 of 2x plus 3. Now, notice that this is a positive logarithm, right? I don't have to write the plus out here, but it's positive. It's going to end up in the numerator of my fraction. Anything that is negative or being subtracted is going to end up in the denominator. And so this is going to become log base 10. This was positive, it stays in the numerator. X minus 1 to the third power. These were negatives though, so they're going to end up in the denominator, x to the 1/3. And they're both going to be in the denominator, and they'll both be multiplied. And so this is going to be 2x plus 3. Okay. Now the last thing I'd like to do is the fractional exponents. Sometimes they're good, sometimes they're not. The book wants me to rewrite this as cubed root rather than x to the 1/3 power. And so remember that anytime we have an exponent that's a fraction, the denominator becomes the index of the root. And so this is the answer that the book has. There are two more properties that are very useful in logarithms. The first one says that if we have the log base a of an exponential that has the same base, right, so the base of the logarithm is a and the base of the exponential here is also a, that the log base a and the base a cancel, and we're going to be left with just the exponent, which is x. The other one says that if we take a and we raise it to the power of log base a of x, that a and the log base a cancel, and we're going to be left with the argument of x. And so to prove this one, we're going to start by saying, and I think you can agree, that a to the x is equal to a to the x, right? They're equal, they're the same. And so we can write this in a logarithmic form. This is going to say that log base a of a to the x is equal to x, right? And so I just followed the rules for changing an exponential equation into a logarithmic equation, and this is what the identity says. And so anytime, and I'm sorry, I made a big mistake here. The base is supposed to be a, not x. This is log base a of a to the x should be equal to the exponent x. And so anytime we have log base a of a to some power, and a can be any real number, the log base a and the a cancel, and the answer is just whatever the exponent was. Over here to prove this one, we'll start with the identity that log base a of x is equal to the log base a of x, right? And so they're exactly the same, they're equal. And to prove this, we will rewrite this in an exponential form, which says that the base a to this power, log base a of x, is equal to the argument of the logarithm. And that's exactly what the identity says. And so again, if we have the base a raised to a logarithm of the same base a, the a base and the logarithm base a will cancel, and we're going to be left with that argument, which is x. And so here, the logarithm of a cancels the a, and we're just going to be left with x. Here the a and the logarithm base a cancel, and again we'll be just left with x. So let's look at some examples where we apply those last two properties. The first one is example 5. It says find the value of log base 2 of 16. And so log base 2 of 16, we can simplify this sum by saying that 16 is 2 to the 4th power. And I think you'll agree that 2 to the 4th is 2 times 2 times 2 times 2, which is in fact 16. And so 16 is 2 to the 4th power. And since we're taking the logarithm of base 2, and the base of the argument of the logarithm is also 2, the logarithm, base 2, and the base of 2 cancel, and we're going to be left with 4. And so the log base 2 of 16 is equal to 4. And we can check our answer by rewriting this in an exponential form. This says that 2 to the 4th power is equal to 16. And we already proved that. And so this will be the solution to that problem. This is example 6. It says find the value of log base 10 of 0.01. And so the log of base 10 of 0.01, this is the same as log base 10 of 10 to the negative 2 power. And so remember that something like 10 to the negative 2 power, where the exponent is negative, is the same as 1 divided by 10 to the positive 2 power. So we can put this in the denominator and change the sign of the exponent. and this is going to be 1 over 100, or 1/100th, which is exactly what this decimal says, 1/100th. And so 0.01 is the same thing as 10 to the negative second power. So since we're taking log base 10 of 10 to some power, the log base 10 and 10 cancel because they're the same, and we're going to be left with -2. And so log base 10 of 0.01 will be equal to -2. And again, we can check our answer. This says that 10 to the -2 power is equal to 0.01, and we've already proven that that'll be the case. This is example 7. It says find the value of 5 to the power of log base 5 of 8. And so one of the properties we had said that if we have a number being raised to a power, and the power has a logarithm in it, and the base of that logarithm is the same as the base that we're raising to that power, that they cancel. And so for 5 to the power of log base 5 of 8, the 5 and the log base 5 cancel, and we're left with 8. And so 5 to the log 5 base 5/8 power is just equal to 8. They just simply cancel. This is example 8. It says find the value of 9 to the power of log base 3/25. And so to solve this, we have to recognize that if the base matched the base of the logarithm and the exponent, that we could probably make something cancel. And so 9 can be the same as a 3 if we write it as 3 squared. And so we can rewrite 9 log base 3 of 25. That is the same thing as 3 squared. And that is 9. And all of that is being raised to the power of log base 3 of 25. And so when we raise a power to a power, we just multiply the exponents together. And so this will be the same as 3 to the 2 times log base 3/25 power. And here we can apply the property that says that if we have a multiplier outside of a logarithm, that becomes the exponent. And so this would be the same thing as 3 to the power of log base 3/25 squared. Right, so the multiplier outside the log becomes the exponent. Now the base is 3. It's being raised to the power of a logarithm of base 3. They will cancel. And all we'll be left with is 25 squared. And 25 squared is 25 times 25, which is 625. Example 9 says find the value of log base 2 of 8 to the power of log base 2, 8. And so we want to, again, recognize that 8 is a power of 2. And so if we can rewrite this 8 as 2 to some power, this log base 2 and that 2 to some power will cancel and we'll be left with the exponent. So what I mean is, if we're taking log base 2 of 8 to the power of log base 2, if I rewrite 8 as 2 to the third power, because 2 times 2 times 2 is 8, that's going to make the log base 2 and the 2 cancel. Right? So anytime we take the log of some base of a number that is the same as that base, it cancels and we're going to be left with just the exponent. And so this simplifies to be log base 2 of 8. The log base 2 and the 2 cancel, and I'm going to be left with to the third power. Okay, so this is going to be log base 2 of 8 to the third power. And then I have log base 2, and I have 8 to some power. Again, I need to be able to recognize that 8 is 2 to a power. And so I want to rewrite this as log base 2. Instead of writing 8, I want to write 2 to the third power. Right? That's 8. And that is all being raised to the third power. Okay? And so the rule for exponents, again, when we have a exponential being raised to another power, we multiply the exponents. So the log of base 2 of 2 to the third power raised to the third power is going to be 2 to the 9th. And now I have log base 2 of 2 to some power. The log base 2 and the 2 cancel, and we're going to be left with just 9. And so the log of base 2 of 8 to the log base 2 to the 8th power is equal to 9.